Now we're going to take a look at what the length or the norm of a vector is. So we'll often use the word norm for vectors, but it really means the same thing as the length or the magnitude of the vector. Why do we need this? So recall that we're trying to find the angle between two vectors, and we're trying to do this because ultimately we want to find the projection of a vector onto another vector. So if I have two vectors and I want to find the angle between them, how we're going to do this? Well, we're going to be using the law of cosines to get what theta is. And to do this, we're going to create a triangle using vectors u and v. We're going to first position our vectors so that they start at the same place. And then we're going to add this vector to the diagram, which is the vector v minus u. And that will create a triangle. That's not necessarily a right triangle, but it will create a triangle. And using the law of cosines, if we know the length of all of the sides of the triangle, we're going to be able to use the law of cosines to solve for theta in the equation, and therefore get the angle theta. So that's why we want to find the length of a vector. Okay, so we're going to start by finding the length with a vector in 2 space, and that's not very difficult. And then we're going to move to 3 space, and ultimately I'll show you a way to calculate the length for a vector that is in n space, or Rn. So 2 space is the same thing as R2. So this is the Cartesian plane, so R2. This is x, the x and y. And imagine I've got a vector u, which is this vector, with coordinates u1, u2. So what I'm trying to get is a formula that will give me the length of u based on the values of u1 and u2. So for example, if u is the vector with coordinates 3 and 7, I want to have a formula for the length that will involve the number 3 and 7. Okay? So 3, 7 is a specific case, so I want to have a general formula, so I'm going to keep arbitrary values for the coordinates of u. So what does that mean? It means that this side here is u1 and this side here is u2, and what do I have here? I have a right triangle. So I can apply the Pythagorean Theorem. Now I'm going to need a notation for the length of u. That's going to be called a norm. So maybe let's write that notation. Okay. The length of u, so instead of writing that all the time, that's too long. Okay, so by definition, we're going to call this the norm of u, but that's still, we haven't made any progress. We just relabeled length for norm. So the symbol we're going to use for this is this. It's kind of like an absolute value symbol around u, but it's the bars are doubled. Okay, and why is this? It's because there's an analogy between the absolute value and the norm. If you've got the real line and you've got, I don't know, numbers on the real line, we can think about these numbers in terms of points, but also in terms of vectors. So if you draw, you could also associate a vector to every point, a vector that starts at the origin. Okay, so what we call a position vector, and there'd be another one here for the point -2. So here I have two vectors on the real line. They each have a length, and what's the length of these vectors? That's exactly what we call the absolute value. Right, so the length of -2 of their vector -2. If you think now of the number minus 2 or the point minus 2 as a vector, its length is 2. And the length of 3 is 3, right? And that's given by the absolute value. So that's why we're using, with vectors, we're using the double bars, but and sometimes in books you'll even find this. Okay, they really use the same symbol as the absolute value. That's because the absolute value is kind of like a special case of the length of a vector in one space or in one dimension. So, going back to my diagram, I can write normal view here. So according to the Pythagorean theorem, the hypotenuse squared, okay, which is normal view squared, is going to be the sum of the square of each side. And if I want to have an expression just for the length, just for normal view, I'm going to take the square root on both sides, and taking the square root, this just becomes normal view, because the norms or the length is a positive quantity. So when you take the square root of something positive that's squared, you just get that positive value. So here normal view, and on the other side we get this. So this is our first formula. The normal view for a vector in, whoops, I forgot the square here, for a vector in 2 space is the square root of u1 squared plus u2 squared. Just be careful, the 2 up there is for squaring something, and the 1 and the 2 at the bottom, those are they're used to specify the coordinates of the vector. Okay. Now in 3 space, it's a bit more difficult to illustrate, and that's R3, right? So it's more difficult to illustrate what's happening here, because I need to draw a vector in 3 space. So I'll try to do my best. So first I have the 3 axes, and I have X here usually, Y and Z. So usually you draw the YZ plane on the page, and X is kind of pointing towards you from the screen. So because we can't do that by drawing something in 2D, we're gonna have the x-axis slightly slanted, so to give the illusion that it's coming at us. Okay. Okay, so now imagine I have a vector with whose first coordinate is u1, okay, and then its second coordinate is maybe u2, okay. So its shadow onto the xy plane would be this line that I'm currently drawing. And imagine it has a third component u3, so maybe u3 is like this, right? u3. So I need to make, okay. So this is u3. Maybe I'll use a different color for u3 because you won't see anything. This is u3. So these two, they should have the same length. So my vector is this. That's u. Okay, and the dotted line in the xy plane, this dotted line, that's the shadow of u on 2xy. Okay. So two things to notice. Well, maybe I'll redraw this so that I can remove some of the things that I've labeled on the diagram, so that you can have a clearer idea of what's going on. Okay, now there are two triangles I want to look at. This one, and because this side here, that's the projection of u onto the xy plane. This is actually a right angle. It's kind of hard to see, but if you think about it for a second, we're going this side here is going straight up, so it's making a right angle with the xy plane. So I've got a right right angle triangle here, and I've got another one right here as well. So this is also a right angle here. So this is also a right angle triangle. Okay, I'm going to play with these two triangles. So first of all, I'm going to maybe define some of the vertices that are kind of important for me on this figure. So this is Q, R, up there this is P, okay, and this one maybe O for origin, okay. And I'm gonna, since I have two right angle triangles, I'm gonna be using the Pythagorean theorem twice. So recall this is U, right? So if I'm looking at the red triangle, okay, so I've got norm of U. Well, I've got this side which is U, so its length is norm of U. This is P here, this is R, this is O. So if I apply the Pythagorean theorem, the hypotenuse squared, so the hypotenuse is OP. So norm of U is norm of OP. Okay. Now norm of OP squared, that's the sum of OR squared and PR. So those are all vectors, right? PR squared. So that's the Pythagorean theorem on the red triangle. Okay, now OR, it's also part of the other triangle. So let me draw it here. The other triangle is like that. So you've got R here, you've got O and Q. Now OR, that's the hypotenuse, right? So the hypotenuse squared, so OR squared, so this part here, I can write it as the sum of the other two sides squared. So OQ squared plus QR, norm of QR squared, and the last term here, I'm going to repeat it, just PR squared. Okay, and let's take a look at what's the norm of OQ. OQ is right here on the diagram. So OQ is what we call U1. Aha. So it's U1 squared. Well, well, you might say, well, actually U1 could be negative, so the norm of OQ is something that's positive, but everything's squared eventually, so it doesn't matter whether U1 is a positive or a negative term, and eventually it's squared, so when we square it, we do get something positive anyway. QR is where? QR is this, that's U2, it's this side, right? These two sides, they match. So U2 squared, and what's PR? PR is this. Oops, no, I thought I had, okay. Yeah, okay, PR is, oh, it's just because the colors overlap. That's PR, and PR matches this, right? So PR is U3. And we've got a beautiful formula. So in 3 space, norm of U squared, that's just U1 squared plus U2 squared plus U3 squared, and if we square root everything, the norm of U is just the square root of U1 squared plus U2 squared plus U3 squared. And look how nice it looks if we compare it to the formula in 2 space. In 2 space, we just don't have the term U3 squared, but you see how this goes. We just added U3 squared underneath the square root, okay? And it's not too hard to prove that in Rn, if I have a vector U with n coordinates, so U1, U2, U3, Un, okay, if I take its norm, it's very simple. It's going to be U1 squared plus U2 squared all the way to un squared. So maybe a quick example, if I have a vector u with coordinates 7, -3, and 4, the length of u, which is its norm, is simply obtained by taking the square root of 7 squared plus -3 squared plus 4 squared. So that would be what? That would be square root of 49 plus 9 plus 16. So that's square root of 74.